right, in the last couple of videos, we talked a little bit about formal proofs. Here, I'm going to work with the same associative property for vector addition, but I'm just going to illustrate it. Now, I'm illustrating this here in 2-space because I've got 3 different vectors and they lie in the same plane. And in general, that can happen in 3-space, but if I'm in 3-space, it's entirely possible that 3 vectors would not lie in the same plane. So I'm going to illustrate this here in 2-space, assuming that they are actually in the same plane, although the principle certainly holds in 3-space, it's just harder to draw. Okay, so the reason this is not going to be a formal proof is because in drawing these vectors, I've made specific choices. In particular, none of the vectors is the 0 vector. A is longer than B and C. None of the vectors is parallel to any of the others. Now, we haven't formally defined parallel, but I think we can agree that none of these vectors is parallel to any of the others. Turns out 2 vectors are parallel if they have the same or the opposite direction. If I were to take a vector, if I extend it infinitely far in both directions, its direction and the opposite, it determines a line. And basically, we're going to say that 2 vectors are parallel if the lines they determine are parallel. Okay. Not super important for this proof, but the fact that none of these vectors is parallel to the others is a choice that I've made. Okay. So to illustrate this, I'm just going to work out the sum that I get on both sides. So working with the left-hand side, I would start by saying, let's calculate A plus B. So to do that, I need to take B and translate it so that its tail is at the tip of A. And then I can say, okay, the vector that points from the tail of A to the tip of this translated B, that's my A plus B. Okay. Now I need to add to that C. So I need to take C and I need to translate it so that its tail is at the tip of A plus B. Okay. And then my vector sum is going to be the vector that points from the tail of A plus B and points to the tip of C. So this vector right here is A plus B plus C. Now I'm going to work out the right-hand side. Okay. In order to see that I end up at the same place, I'm going to work it out on the same picture. Now, a sad consequence of that is that it's going to get a little bit crowded. We'll just deal, but that is one drawback to this. Okay. So here, we do parentheses first. So I would have to do B plus C first. Okay. So that means I'm going to take C, and I'm going to translate it so that I put its tail at the tip of B. Okay, so there's my vector C. I think it does help to have different colors here. So didn't think to tell you this at the start of this video, but if you want to pause and go get some different colored pens or something, might be a good idea. Okay, so now I can say the vector that points from the tail of B to the tip of the translated C, this vector right here, that's my B plus C. And now I need to take A and I need to add this to it. Okay, so here's my A. I need to translate B plus C so that I'm putting it with its tail at the tip of A. So there's my B plus C in translated position. And now the vector that I'm going to get points from the tail of A to the tip of the translated B plus C so that it points to here. Oh, that's the same vector that I just drew that I called A plus B plus C. Now, like I said, this isn't a formal proof, but sometimes drawing the picture can help people understand things more than the formal proof does. So this only shows that it works for these 3 vectors, but I can sort of imagine how this would generalize to other situations and other vectors pointing in other directions with other magnitudes. So this is a very useful tool. I just don't want you to confuse it with a formal proof.